Dear colleagues, I hope you are not too tired. I will try to be less long than I'm usually. So let's see the topic: standardization of building integrated PV, analytical and measuring technical needs for that. Just a few words as introduction. My presentation will be different than previous presentation because exactly it is not dealing about general, I mean, standards, kind of standards, but it is a part of my, let's say, search and an initiative to start really seriously, internationally, globally, to work in search for one standard and standardization procedure for building integrated PV. Early photovoltaic, just a little bit of history. The term photovoltaic PV combines the Greek phos and light, volt, Alessandro Volta, pretty long ago. PV effect at first observed early in 1887 by Heinrich Hertz, followed then series of experiments, John Thomson, Charles Fritz, Edward Wesson, and there was also the first US patent for solar even in 1988. Here Nikola Tesla's name is also to be mentioned for method and apparatus for the utilization of radiant energy, and the number of that standard is 190. Philip Leonard later found that the intensity of the incident light has no effect on the maximum kinetic energy of the photon electrons. And Einstein Nobel Award was for me really exciting to learn. Later experiments did show that frequencies below a certain cutoff value, threshold frequency, would not eject photoelectrons from the metal surface independently how bright the source is, contra to the classical model of light in that time, which was well. New science advance was necessary, and it was reached by the world's most famous physicist Albert Einstein in 1905. Einstein did recognize that Planck's contrivance was in fact a rational description of reality. In 1905 he wrote, "What we perceive as a continuous wave of electromagnetic radiation is in reality a stream of discrete particles." And exactly that part was supported by Nikola Tesla studies research. So Nobel Prize in Physics 1921 was given to Einstein for his, let's spread the real definition, services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. I didn't know about that, also there are so many writing about Albert Einstein. There are so many really attractive buildings with building integrated PV, designed and constructed and in use around the world. Left above, that's I think Times Square in New York, and that was refurbishment of one existing building. Down left might be Near East, in the middle India, and right China. From building integrated PV to building component, that is a way. Building integrated PV is PV material, layer, just layer used on building, replacing exactly traditional layers, building envelope of the envelope structure. Buildings applied in buildings integrated PV, thermal hybrid PVT system, growth of construction and utilization worldwide. Architecture and engineering sciences, art, maturity is also reached, very much improved. Operational and maintenance experience is gained and is in growth. Performance and useful energy data collected from many locations and many kinds and types of buildings around the world. Commercialization, industry and market in enormous growth. Enormous growth, but in not continuous linear growth, but with waves. Huge intensity of growth, then certain decrease. And there is nearly again one of period when huge increase of industry manufacturing capacities was reached, but not as expected exactly explanation, as expected implementation. So despite all mentioned building integrated PV still is not used on large scale in buildings and often are not considered at all by architect and designer and also some investor as a further option in their project. Just illustration, building integrated PV versus PV, non-standard component, there are very different kinds of facade and part of envelope implementation, also roof, different types of materials also used. Very attractive designs, buildings all around the world. If we are comparing building integrated PV versus PV as a non-standard component, conventional or standard PV modules, worldwide product the same. In Switzerland, there is Italy, US, China, so let's say decontextualized, built or produced electricity at low price. Same requirement worldwide, also different climates, conditions, or applications. Standard size, no building, easy to carry but fragile, all the same. Industrial mass production, substructure optimized for the model, cheap, and so on. Here down, I have also one cross-section of layer with building integrated PV. But you see, there is, I think Peter will like that, and maybe Olivia. But that is exactly the drawing, a part of his exegetic explanation about use of PV, of Bureau Kyrgyz for Turkey. So, you know, a part of incinerator PV is converted and produced electricity, and there is a part which is released as a heat to the surrounding, what is in accordance with the second law of thermodynamics. That heat can be used further for thermal purposes, but also again to produce electricity using thermoelectric effect. So that will be even higher and better use of more produced energy, electrical energy of higher exergy. There is interesting, I had a communication, and we did organize one as a technical committee for solar energy utilization of Russia in Orlando conference. We had presentations from Switzerland, from Europe and US and Far East. Swiss building integrated PV focus is very interesting. Planning regulations against urban sprawl. So at the level of government, where they are very carefully planning how they are going to use this type of energy conversion. They have approximately building applied PV, 75%, and 25% building integrated PV. In Switzerland, no PV power plants are permitted. So it is not permitted to construct power plants. It is not a big country. They don't want to simply reduce the green surface in the country. So it is not permitted. So only can build integrated on buildings. I think for Serbia it should be also the rule, because Serbia is not so big country and is to keep on greenery. It is huge solar power plants are for deserts. Architectural design as innovation, demonstration of PV into various building envelope elements, zero CO2 emission buildings or zero fossil energy building, performance validation through measurements, building integrated modeling and planning. That's all is what they are working and addressing in their technology research and development. Concerning building integrated PV and generally concerning PV system, the efficiency of conversion of solar radiation, energy of solar radiation to electricity is very dependent on the temperature, and there is approximately about 25 degrees the optimal temperature for getting highest efficiency of this conversion. It's just illustration about dynamics of change of conversion of energy efficiency during the operation of photovoltaic chain and in versus irradiance, also variation of change of solar radiation. Here is also illustration how exactly the same PV module placed on the different surfaces and a different way can have different temperatures, and naturally also the same model work and has very different efficiencies. Here is a cross section of one wall with the PV photovoltaic on the second facade, and it is, you see, in this space between the opaque wall and the second facade and PV. On that facade there is air space, and this space, if we have, like here, 4 seasons, then in summer, to keep the optimal temperature of this PV layer, it will be necessary to remove that heat, and so it will be this open, down and up. And in winter, this heat could be used for just preheating, ventilation, fresh air. Here are all, marked heat transfer processes, solar radiation, radiative heat exchange between PV and opaque wall, convection and the radiative losses to the environment, heat conduction, and everything. Natural here is to be also added, and or it is within, definitely, but not just specifically here marked, that this heat, which is not converted to electricity, but also is released to this air in. When building integrated PV, we have as a layer, and it is a layer in building envelope structure, to get one relevant standard, we have for building to have all features and all, physical data on heat conduction, heat transmission, and so on, as we have for building other structures, other layers of the building envelope. For example, solar heat gain coefficient. That is one very important for glazing, that is also very important for opaque wall, and it is also to be determined for photovoltaic glazing. And this is just, for example, this is section of calorimetric hot box system for solar heat gain coefficient measurement. So this is just a scheme of system, and here in special indoor control conditions with solar simulator are to be the measurement done on specially defined, like it's always done in different standards. So it's just one example how one very important feature is to be done and nobody till now is yet doing. There are many measurements in many laboratories all around the world, but mainly all those also, although with a pretty big investment, experiments are dealing with certain room or just part of building oriented in different direction, measuring behavior and of that space for that building, for that occasion, but not exactly at the same time measuring relevant properties of that room, of that built space. So they're measuring cooling and heating energy performance, electrical energy production, glare test reference, illuminance, metrics of success, mainly result measurable reduction in cooling load energy, electrical energy production, and so on, but not specific feature of that layer of the structure. What is European situation? IEC versus construction product regulation. Building integrated PV is both a PV element and construction component. Presently, there is no harmonized standard specific for building integrated PV. Jack just confirmed to me. Now there is one. Presently, instead, we have electrotechnical framework and the building construction framework. So far, 99% of building integrated PV modules have no CE mark according to the construction product regulation CPR. Some countries have their own rules, has one with the DIPT. With the European situation more, what exactly and generally that kind of standard for the whole complete standardization of building integrated PV should have. It should have all relevant features concerning mechanical resistance, definitely, fire safety, hygiene, health and environment, safety in use, noise, energy economy, and heat rejection, sustainability, just to list a few. There is this number 5583, photovoltaic in buildings. The standard introduces tests on the wall system like wind resistance, uplift, rain penetration, snow resistance of the wall structure. In that sense, some also research papers are coming to energy and building. There's mechanical test on roof system and Swiss PV module test that is one center in Switzerland, so that's there. So what should be improved? There is almost no coordination between the certain working groups, and 50583 is approved and cover all possible installation, but it does not provide any further test for building integrated PV module apart from rain penetration test and uplift resistance test for PV tiles. Some EU countries have more restrictions for building integrated PV since it is not a regular building product, Germany and things. More illustrations. Very interesting. That was already said. What is more about this situation? Current IEC, UL, and C qualification tests are performed on the new or near new models, not repeated on rather aged products. Therefore, their property retention characteristics are unknown. Current IEC qualification tests are primarily go, no go, they say that way in this Swiss center. Kind of test for infant mortality and initial pass, fail, reliability, and do not test or assure long-term durability or aging characteristics. Design qualification and type approval of PV nodules according to the electrotechnical standards, and here number 61215 and 61646 cannot provide the required material residence because the included mechanical load test is carried only once, testing only one module, and no ultimate load is determined which would lead to breakage. So they are all missing very important issues. Now, that is what I did find with these colleagues from Switzerland, what is missing. And here I will just present you a little bit on our research, my colleagues, what we are trying to do. And it is related to the determination of special features and explanation, and provided with this performance possibility to calculate what is necessary when we are designing, when we are optimizing building, concerning building integrated PV, so heating, cooling, loads, but also indoor environment quality, so mathematical simulation and optimization necessary for design. So here we have like in summer configuration, PV, glazing, and there is first window and indoor space. And in summer, here we have just circulation, balancing natural flow and convection and absorption of released heat of PV. In winter, we have this situation that this released heat, not converted to electricity of PV, is accepted, absorbed by airflow and flow of fresh ventilation air, and on that way reducing heat, reducing loads of the building. For building performance simulation and optimization and determination of indoor also air conditions, we are using building total performance optimization, so energy simulation, and also using CFD, defining and calculating the flow, so it is co-simulation. This was on this way on PhD thesis done, building energy simulation and CFD coupling goals. Energy simulation depends on airflow definition in simulation. Energy simulation depends on convective heat transfer coefficient. So when we are using either one of programs for building energy simulation, Energy Plus, or Transis, or SPR, or some other, we are using only energy simulation on that program, accepting heat transfer coefficients. So, which are just constant values. But using CFD, we are trying to calculate, starting with windows, I'll just show later, and to come to the surface of the building and get real velocity and calculate and determine real heat transfer coefficient. And so to develop that kind of software and model, building energy and CFD co-simulation, internal and external coupling can be combined, can be used, and in this PhD thesis and now with PV is external coupling in use. So that is kind of schematic presentation of this development. Every step is calculated until the full convergence. And here is our comparison of obtained result with this finished thesis, not with PV, but now we are doing with PV, not yet the result. So you can see that just with energy simulation, we have these temperatures determined that they will be in indoor space. Using combined building energy and CFD, so co-simulation, we have these red, and these blue are measured values. So it is very clear that this way it is possible really to determine much, much better and closer indoor conditions, indoor thermal conditions, and we have never to forget that energy efficiency and renewable and all kind of optimization, and never to forget that quality of air and health of people is important. Just in bigger, the same picture, and that was just illustration of these final results and the whole process of this thesis. So it was a residential building with cross ventilation and with atrium and simulation from at first a block of buildings starting with windrows was done, and we got all necessary values of velocities and pressure at the outside surface of the building, and based on that, even the goal of that thesis was exactly to determine the necessary moments when from natural ventilation and different floor is necessary to change and turn on mechanical ventilation to solve that problem, and that was this way determined. So velocities of different levels, and comparing those velocities of air with the determination of fresh air entrance to the space, and determination when the moment when it is necessary to turn on mechanical ventilation. Even very sensitive low pressure difference sensor was developed, so based on the difference of pressure difference on the ground to the certain level, when it is lower than it is necessary, then it is activated change to mechanical ventilation. Now with the building integrated PV, with the same process of study and research is in realization, and that is scheme of the calculation which was, and the graphical, the physical model of this study which was done. And this was a result, so there was not only on the entrance but also even when it is open window, indoor, how the velocities are distributed. So, final comments about building integrated PV, CFD and BESS, or co-simulation. That's really very useful. It can provide architectural modeling and energy efficiency optimization framework, safety analysis generally restricting to the building's environment flows, designed by supply boundary condition. And this study dynamically describes the boundary condition and applies the building integrated PV via integrated CFD and BESS modeling to optimize indoor environment quality and building's energy efficiency of one residential building block. So this study, when we finish it, will really provide all those necessary data. Conclusion for this presentation is a study building integrated PV and ISO, IEC standard need. That is, all these investigations shows that this standard need as this integral building component is really necessary, and globally building integrated PV, the electricity producing modules are both a functional unit of the finished buildings and yet also a construction element of the building scheme, replacing conventional materials. This affects new builds as well as economically significant retrofit segment and energy refurbishment. The potential to become an industry leading reliable, renewable energy plus cost-effective energy source. Most investors, planners, architects and builders still find the practical implementation of available building PV solution difficult, and there is often both a considerable lack of awareness and a persistent resistance among stakeholders toward these matters. This technical committee solar energy utilization, just in previous junior NATO conference, have this seminar, solar energy utilization seminar but forum, and as building integrated PV is a cutting-edge technology, needs relevant working group and plan for preparation of an international building integrated PV standard, globally acceptable concerning building integrated PV technologies, technical requirements of both buildings, construction, industry and electronic industries. It is to be developed a scientifically, technically sound document with all relevant data and measuring technical specifications necessary for globally reliable building integrated PV design, construction, testing, commissioning, and operation. TCs encompass all relevant fields and could have crucial role in international building integrated PV standardization. And for example, there are these committees that were present also on this fair forum. So there is group, organizing group of standards, guidelines, codes. There is technical committee electrical systems, so it's part of their duty. Then solar energy utilization, initiator. Then integrated building design, definitely is also responsible. Exergy analysis is also for sustainable building. And also other sponsoring committees, load calculation data and procedures, building materials and building envelope, structures, performance, then fenestration and energy calculations. So there is a lot of work to be done, but I think it will be very, I think, important and valuable to do as soon as possible. Thank you very much.